But sometimes it won't be as obvious. So let's look at CrO4, the 2- version here, so a chromate ion. And if we draw the skeletal structure, we have 4 things that the chromate needs to bond to. So let's do the Lewis structure again. When we figure out the valence electrons we have 6 from the chromium. We have 6 from each of the different oxygens. And where did this 2 come from? Yep, the negative charge. So remember, we have 2 extra electrons hanging out in our molecule, so we need to include those. We have a total of 32. 40 are needed to fill up octets. So again, we have 8 bonding electrons available, so we can go ahead and fill these in between each of the bonds. What happens is that we then have 24 lone pair electrons left, and we can fill those in like this. And the problem comes now when we figure out the formal charge. So when we do that, what we find is that the chromium has a formal charge of +1, and that each of the oxygens has a total charge of -1. So we actually have a bit of charge separation here. Without even doing a calculation, what is the total charge of these that are added up? Okay, it's -2, that's right. We know that the total charge of each of the formal charges has to add up to -2 because that's the charge in our molecule. We can also just calculate it. The chromate gives us a +2. Then we have 4 times -1 for each of the oxygens. So we have a -2. So we have some charge separation here. And in some cases, if we're not at n equals 3 or higher, there's really nothing we can do about it. This would be the best structure we can do. But since we have these d orbitals available, we can use them. And it turns out that experimentally, this is what's found, that the length and the strength are not single bonds, but they're actually something between a single bond and a double bond. So how do we get a 1.5 bond, for example? What's the term that lets us do that? Resonance, that's right. So that's exactly what's happening here. So if we went ahead and drew this structure here, where we have now 2 double bonds and 2 single bonds, that would be in resonance with another structure where we have 2 double bonds instead to these 2 oxygens and now single bonds to these 2 oxygens. We can actually also have several other resonance structures as well. Remember, the definition of a resonance structure is where all the atoms stay the same, but what we can do is move around the electrons. We're moving around those extra 2 electrons that can be in double bonds. So why don't you tell me how many other resonance structures you would expect to see for this chromate ion? All right, let's take 10 more seconds on this. All right, this is good. I know this is a real split response, but the right answer is the one that is indicated in the graph here, that it's 4. This takes a little bit of time to get used to thinking about all the different Lewis structures you can have. So you guys should all go back home if you can't see it immediately right now and try drawing out those 4 other Lewis structures for chromate. There are 4 others. You'll probably get a chance to literally do this example in recitation where you draw out all 4, but it's even better to make sure you understand it before you get to that point. So we can go back to the class notes. So it turns out there's 4 other Lewis structures. So basically, just think about all the other different combinations where you can have single and double bonds, and when you draw those out, you end up with 4. So for every single one of these Lewis structures, we could figure out what the formal charges are, and what we would find is that it's 0 on the chromium, it's 0 for the double bonded oxygens, and it's going to be -1 for the single bonded oxygens. So what you can see is that in this situation, we end up having less formal charge separation. And that's what we're looking for. That's the more stable structure. So anytime you can have an expanded octet, an expanded valence shell, where you have n is equal to or greater than 3, and by expanding and adding more electrons into that valence shell, you lower the charge separation, you want to do that. I also want to point out I basically said there's 6 different ways we can draw this in terms of drawing all the resonance structures. You might be wondering if you have to figure out the formal charge for each structure individually, and the answer is no. You can pick any single structure and the formal charges will work out the same. So for example, if you pick this structure and your friend picks this structure, you'll both get the right answer, that there's just the -1 on the oxygens and no other formal charges in the molecule.